Welcome to next lesson in magnetic fields in matter. Here we will discuss the remaining portion of the last lesson. In the last lesson, we have discussed the linear magnetic materials. And we found that in linear magnetic materials, the magnetization M and the magnetic field B, both of them are proportional to the auxiliary field H. M is equal to chi m into H, where chi m is called a magnetic susceptibility, and B equal to mu into H, where mu is called a magnetic permeability. And we have seen that diamagnetic and paramagnetic materials are generally linear materials. In paramagnetic materials, chi m is small and positive, and mu is a little greater than mu 0, where mu 0 is the permeability of free space. And for diamagnetic materials, chi m is small and negative, and mu is a little smaller than mu 0. Now here we are going to discuss the nature of ferromagnetic materials. And we will see that ferromagnetic materials are inherently nonlinear magnetic materials. So ferromagnetism basically arises from the spin magnetic dipole moments of unpaired electrons. So in a sense, this ferromagnetism is similar to the paramagnetism, because both paramagnetism and ferromagnetism are basically from the spins of unpaired electrons. But the important point which discriminates between this paramagnetism and ferromagnetism is the nature of interaction between the dipoles. In a paramagnetic material, the individual spin dipole moments are independent. They are not interacting with each other. So if we apply a magnetic field, that field can easily rotate the individual dipoles so as to align them parallel to the field. But in the case of ferromagnetic materials, even in the absence of any magnetic field, the individual dipoles are strongly interacting. This interaction is a quantum mechanical effect. And this interaction makes ferromagnetism much different from paramagnetism. This strong interaction between the individual spins makes the nearby dipoles aligned in the same direction. So they get aligned in the same direction in a region, and that region is called a domain. So in ferromagnetic materials, there will be different domains. Each domain will have dipoles aligned in a particular direction. Another difference is the magnetization in a ferromagnet is much greater than that in paramagnets, because the susceptibility of paramagnetic material is typically 10 raised to minus 3 or 10 raised to minus 4. Whereas the susceptibility of a ferromagnetic material is 10 raised to plus 3. It is several orders of magnitude greater than paramagnetic material. Another important difference is the ferromagnetic materials has the ability to keep their magnetism even if the external field is removed. So they can act as permanent magnet. But in paramagnetic and diamagnetic materials, they will lose the magnetism immediately after the external field is removed. So in short, we can say that ferromagnets are nonlinear magnetic materials. They are nonlinear because their susceptibility chi and their permeability mu are not constants. They will depend on the external field. So the relation between M and H will not be linear, and relation between B and H is also not linear. So they are called nonlinear magnetic materials. Now, what is the case in an unmagnetized ferromagnetic material? There are basically 3 ferromagnetic materials in elemental form. They are iron, cobalt, and nickel. If we take an iron bar, we cannot see any magnetism in that iron bar, although it is ferromagnetic. So what is the reason? Inside a ferromagnetic material, there will be different domains, and each domain will contain millions of atoms. So these domains, in each domain, the dipoles are aligned in a particular direction. So here, this is a domain in which dipoles are arranged in the direction of this arrow. So inside each domain, there is an arrow. That arrow represents the direction of dipoles in that domain. So all dipoles in that domain will be aligned in that particular direction. But as a whole, in the bulk of the material, the domains are randomly oriented. So the material as a whole has no magnetic property if it is not magnetized originally. And remember one point, the magnetism in ferromagnetic material depends on the history of magnetization also. What is meant by this history? It will be explained after a few moments. Now what happens if a magnetic field is applied? If a magnetic field is applied, then a torque M cross B acts on individual dipoles. In a paramagnetic material, the torque was very easy. The work of the torque was very easy because each dipole can be rotated very easily. But here, the task in front of the torque is very difficult because the dipoles are strongly interacting. So the dipoles well inside a domain resist this torque. This torque cannot rotate an individual dipole because the torque has to rotate the whole dipole together because the dipoles are interacting, but it is not possible. So what happens is, at the boundary, there are some boundaries are there between individual domains. If you apply a magnetic field, say, in a particular direction, there will be some domains which are oriented in the direction of the applied field. For example, if you apply a magnetic field from the bottom left corner to the top right corner in this direction along the diagonal direction, then the dipoles of this domain and also this domain and also this domain and also this domain, they are arranged in the same direction. But these dipoles and also this one, also this one, they are arranged in another direction. So there will be a tug of war between the dipoles at the boundary between two domains. And those domains which are aligned parallel to the applied field will be favorably oriented, and the dipoles in the opposite direction will be turned by this torque, thereby increasing the boundary of these domains. So this is called the increase in the boundary area, or the boundary will be increased. So the individual dipoles at the boundary between two domains, the torque converts dipoles from the less favorably oriented domains to the more favorably oriented domains. More favorably oriented means to the domains which are parallel to the applied field. So the domains parallel to the field grow in size, whereas others shrink in size. So what happens is, if we increase here, the graph shows the variation of magnetization versus the magnetizing field H. And the magnetizing field is proportional to the current I. So this graph represents current versus magnetization. And where is this current means? We are magnetizing an iron rod by placing it inside a solenoid. And we are running through that solenoid a current I. So I is defining the magnetizing field H. So this is a I versus M, or you can write H versus M. Anyway, the shape will be same. So originally it is not magnetized. As current increases, the magnetizing field also increases. So the magnetization increases because the domains parallel to the field increases their size, and when the field is very strong, If the field is strong enough, the one domain takes over entirely. That is, all the regions are aligned into a single domain and the material is now said to be saturated. Now if we increase the magnetizing field, we cannot get any increase in magnetization because already all dipoles are aligned in the same direction. Now if we decrease the magnetic field, what happens? When the field is removed, the domains do not shift back completely to their original state because they are again strongly interacting. They cannot go back to the random position as in the case of paramagnetic material. So even when the magnetizing field is removed, if it is zero, some amount of magnetism is retained by the material. This is represented by OQ in the diagram. And the magnetization retained by the material in the absence of applied magnetic field is called the retentivity of the material. Now if you want to demagnetize the material completely, then we have to apply a magnetic field in the opposite direction. So we will increase the magnetic field, that is, we will give a current in the opposite direction in the coil. So the magnetizing field will be in the opposite direction, so that the magnetism gained in the positive sense decreases and it becomes zero at this point. That is at the point R. So OR is the reverse magnetizing field which is to be applied to demagnetize the material completely, and this field is called the coercivity of the material. This is OR in the diagram. Now if we increase the magnetic field again, then the material will get a magnetization in the negative direction and it will go into the negative saturation. And if we switch off the field, the material will come back, but it will retain some magnetism, that is called OT. Again it is called retentivity. Then if you want to demagnetize completely, you have to apply a positive magnetic field so that the material reaches at the point U. So this OU is called the coercivity again. And eventually, if you increase the magnetic field, it will go into the saturation point P. So what you have obtained is a loop. In that loop, it is a loop of I versus M or H versus M, or you can have H versus B. In all these cases, the shape of the loop will be same, and that loop is called the hysteresis loop. So it is the lagging of M behind H or lagging of M behind I. This lagging is represented by the hysteresis loop. And this hysteresis loop also reveals that the magnetization of the material depends on the history of magnetization. History means, for example, at this point, when the magnetic field is this much, you have three possibilities. Either the magnetization may be this value, or it may be a higher positive value, or it may be a negative value. So whether it is negative or smaller positive or higher positive depends on the history of magnetization. History means whether it is coming from the positive saturation or from the negative saturation or from the unmagnetized position. So this is the reason that we can say that the magnetization in a ferromagnetic material depends on the history of the material also. So this is inherently nonlinear. Now for ferromagnetic material, the susceptibility is very high. It is much greater than 1. For paramagnetic and diamagnetic material, it is almost equal to 1. And it is very large. This is also very large. For paramagnetic and diamagnetic materials, it is very small. It is 10 raised to minus 3 or smaller. For one, it is positive, and diamagnetic it is negative. But here it is very large. And in a magnetized material, the magnetization M, the magnetic field B is equal to mu 0 into H plus M. In that case, the magnetization M will be much greater than the magnetizing field H. because chi m will be very large. So we can write this approximately equal to mu 0 m. So in practice, we see that in a ferromagnetic material, the magnetic field B and magnetization M are directly proportional. But we cannot say any proportional relation between B and H or M and H, because chi m and mu, both of them are not constant in the case of ferromagnetic materials, but they are very high. Now there is a particular temperature. The ferromagnetism can keep that property only up to a particular temperature. If the temperature of the material is higher than that, then ferromagnetic material becomes paramagnetic material. That temperature is called a Curie point. So above that Curie point, ferromagnetic material becomes paramagnetic material. An example for iron, this is 770 degrees Celsius. And this transition from ferromagnetic material to paramagnetic material is a phase transition. Phase transition means it is occurring at a fixed particular definite temperature. This is similar to the transition from liquid to solid or solid to vapor, or vapor or liquid to solid, or solid to, or from liquid to vapor state. So this is also a phase transition. So what we have studied in this chapter is the ferromagnetism is inherently nonlinear, and we have studied the hysteresis loop obeyed by the ferromagnetic materials, and these ferromagnetic materials are used for making the permanent magnets. So thank you for watching this video.